In the previous lesson, we implemented a Python-based swerve controller that took twist commands and helped us compute steering angles and wheel speeds for each of the 6 wheels of SHL1. And then we directly published this to the simulation topics. Now that helped us understand the math behind this type of controller, right? But it ran outside the ROS2 control system. So it was just another ROS2 node publishing messages. It was not really part of the real-time control loop. So if we really want to implement something more robust, we need to go from Python prototype to ROS2 control plugin. So let's see why this Python version was not ready for production. So to begin with, a controller should live in the ecosystem of ROS2 control, right? So it should be loaded and managed just by the other controllers by the controller manager. Okay. So the controller manager loads these controllers just like the independent steering and speed controls that we used previously. And then it can request resources through the resource manager. So it can retest state interfaces, command interfaces that connect to the sensors and the actuators of the physical robot, or in our case, the simulated sensors and actuators. Okay, so why the Python controller that we were using previously is not production ready? Well, no real-time execution. So this was just Python code running as a normal ROS2 executor. So the update time isn't guaranteed. So there might be delays, can break controllability. It was outside the ROS2 control, so it doesn't directly integrate with the controller manager or hardware interfaces. It's just another node publishing topics independently. No resource claiming, so there's no real controller to reserve joint interfaces and avoid conflicts. Then there's a disconnect with the real hardware, right? That communicates through CAN or Ethernet CAT or other methods. This was just another node. Performance limits. Python introduces garbage collection and other things that slow things down. So it's unacceptable for tight control loops. So we can't use this Python controller that we use. But it was good for prototyping and understanding the math. Okay. So in order to create an actual controller, we need to create a controller plugin that lives in the actual ROS2 control ecosystem. So we need to create a C++ controller plugin. So there's an excellent article. In fact, here, let me change this from Foxy to master. Okay. There's an excellent article here that we're going to follow, and at the same time we are going to check the code at the same time. So the first thing we need to do here, according to the instructions, is to prepare a package. Okay, prepare a package. So before we had this SHL1 control package, but this was just for our Python code, right? It was just to test the prototype. Now we need another package for the actual controller plugin. So we create this swerve controller package, and then inside of it, we need to have some header and source code. So in the source, we have the source code, and in the include, we have the header files. Then we need to add a header file that follows this structure. Okay, and in particular, we need to create a class that inherits from controller interface. And then we need to make sure to add a constructor with our parameters and override the following methods. Okay, override the following methods that are part of the controller interface class. So if we go to the header, we have our class swerve controller that is actually a controller interface, inherits from that. We have the parameterless constructor, and then we override the different functions or interfaces provided by the controller interface. Okay, so we declare them there, and we say that we're going to override them. And we are going to soon see the actual code. Okay, so then we need to go to the source file and actually add the code. Override the on init, override the on configure, on activate, update, etc. So let's have a look at it. So we go up, and so here the constructor, there's nothing in it, and then on init we are going to declare some parameters. So we have the wheel radius, wheelbase, track width. So pretty much, sorry, we also have the steer joints and drive joints names, okay, strings, and the other parameters are just like in the Python code. And if all goes well, we return success. Okay, and on configure, we actually get the values. Okay, we get the values of these parameters. And let me show you, there's the config file, right, where those values will come from. We're going to see the config file later. So we have these values and also the names of the different joints. And then we do a check. If we don't have 6 joints, we return an error because we expect 6. If everything goes well, we do the same calculations we did in the Python code, right, for the positions of the wheels. So just like in the Python code, we do the calculations for the position of the 6 wheels. We create a list for that. And then we subscribe to the command velocity topic that is of type twist, right? Because we need to get those twists, and then success. Then command interface configuration. Here we are going over all of the steer joint names, and we just configure those names, individuals. So one by one, right? Individual. Configuration type individual for the interface, so individual interfaces for the different steer and drive joints. So we get the names from the parameters. And then we do something similar for the state interface. This is for the feedback, right? The previous one was for the control. This is for the feedback. And again, we use the same names that come from the parameters. Then on activate, we're going to activate everything. So we start by clearing the previous pointers. And then again, we obtain all of the names for position controllers. And then we initialize and we reclaim the interfaces, hardware interfaces, and then the same for velocity controllers. Okay. And then here we are going to initialize a real-time command buffer. Okay, we initialize a real-time command buffer to get twist commands. And then on the activate is kind of like the opposite action. We are first going to set all of the joints to 0 to stop all of the wheels. And then we're going to clear the pointers and we return success. This is when we are stopping everything and deactivating everything. Here's the core update. Here's where we actually run the loop. So here, first we're gonna, from the real-time command buffer, we're gonna read a command velocity. Okay, we read from it, we read a command velocity, which is a twist. And if everything is okay, we extract the linear velocity components, Vx, Vy, and the angular velocity components, omega, z. We initialize the 12 commands, 2 vectors, and then we compute the swerve kinematics, right? And then once we have the swerve kinematics, we don't publish because this is no longer a publisher. We just set the values to the different interfaces, right? So again, this is not a ROS2 node like the Python code. We're not publishing here. We are directly sending these commands through the interfaces to the actuators, and then we return OK. Now, this is the callback for the command velocity, just like the Python code had a callback. This one also has a callback. So again, we go back to where we created the subscriber. And here we see this is a subscriber for command velocity of type twist. Right, type twist. And then we declare the command velocity callback here. So here, every time the callback is executed, because we got a new twist command, we add it to the real-time command buffer, or we write to the buffer. Okay, and this is important to keep things running in real time. And then we read from that buffer in the update, and this update happens like very quickly, like 100 times per second, so 100 hertz. So that's why we need to use this real-time buffer. We cannot rely on the command callback itself. So the real-time buffer will give us always the most up-to-date twist. And then we compute the kinematics. So we receive the velocity command or from the twist, and then we receive the arrays, the list we need to update. Then for every wheel, just the same like Python code, for every wheel we compute, we get the wheel positions, then we compute the velocity of the wheel, then the steering angle from the velocity vector, then the speed, contact speed of the wheel, and then the angular speed at which the wheel should rotate. Just like Python code, exactly the same formulas. Then again, we handle the zero velocity case to stop the wheels. And then we do that optimization to make sure we stay within the negative 90 degrees range. Then we assign the values to the different controllers in the array. And that's it. It's just like the Python code. Okay. Now this is for the code. Now something very important. Well, that's the update thing that we're talking about. But something very important at the end of the file, we need to add this plugin export class macro to make sure that the system ROS understands that this is a plugin and load it accordingly. So here we add this macro to turn this code into a plugin. And then we also need to create a XML file to describe the plugin. So that's the Swerve Controller plugin XML. So here we say the path, the name of the controller, and the base class, which is controller interface, and a short description. So this is necessary for the system to understand that this is a plugin that needs to be loaded. We are going to skip the test. You could write a test, but it's out of the scope of this class. And then we update the CMake list to add the dependencies, and also this very important line here that says that we are a plugin and that should be loaded. So if we look at CMake list, we add the requirements, controller interface, and others. And then this export plugin description to make sure that the system knows that we're a plugin and loads it accordingly. Then this is for test section. We don't have tests. You should have tests, but we're going to skip that for now. And then we go to package XML. And again, here we're going to add some dependencies. So we have a controller interface, hardware interface, all the necessary dependencies, real-time tools, etc., etc. And then we can compile and test the controller. So let's go ahead. Super excited. Let's try to compile and test the controller. So we open our terminal, and so we navigate to the ROS, to the course, not ROS, to the RSC course, ROS2 workspace. We build it if we haven't, and then we're going to launch the whole system. So it's in ROS2 launch. RSA, oh, forget these things. I need to source, sorry. Need to source the workspace. Then ROS2 launch, RSC SHL1, Gazebo, that's where it is. And now we use the Gazebo launcher. Instead of the TP1 or TP2, we use the Gazebo launcher. So Gazebo launch, that has, so we launched, that has the correct configuration. And here we notice that we have the loaded Swerve controller, right? So the Swerve controller has been loaded and configured and activated, okay? So the controller manager took care of it and loaded it, configured it, and activated it. So it's running. So how does it work? So before we had this controller configuration, right? I don't know if you remember, but in this controller configuration, I think it's this one. We had the joints. We had the all steer position controller, and then it was of type forward command controller. We had the all drive velocity controller, and we had the joint state broadcaster, and then for the other position controller, velocity controller, we had to say the joint names, the interface name, and the type. So it was just forward command controller. So we were sending commands directly to each wheel. Okay, and then here in the Python code, we were, as I said, we were directly publishing commands to these independent controllers for each wheel. That was the not so production ready way. In the production ready way, which is this one, we still have the joint state controller, but now we have the swerve controller. Okay, we don't have independent controllers like all drive velocity, joint state there. We don't have all steer position, all drive velocity, six of them for each kind. No, now instead we have one, the state broadcaster, one swerve controller that will get all of these wheel radius, wheelbase, track width, and will get the it corresponds to these parameters, right? These parameters, and then it also gets the steer joint names and the drive joint names, which are read there. We get those values from with this commands. So now we have a single controller that will take care of everything, right? We don't need any, so that's why we don't see the load the all commands, steering commands, or all joint commands. Now we have the swerve controller that takes care of everything, and we don't need that Python code anymore. So now we go to the joystick, and forgetting things. Let's remember history, grab joy, there you go, 1993, command 1993 to launch the joystick. So here's our cool joystick. Let me rearrange these windows. I'm very bad at rearranging windows, so excuse me if I mess things up a little bit. So let me move the windows around. Perhaps I should put this one here. Maybe I should make this one a little bigger. So I'm afraid I'm gonna crash my robot if it's too small. There you go. Okay, so non-holonomic way, right? So standard motion, like a standard little car, and there you go. Look, it's moving. I don't need to launch that Python code anymore. We have a proper ROS2 control plugin that is doing all the computation, all the inverse kinematics don't crash. Yeah, all the inverse kinematics computations, and directly interfacing with the joints. Okay, let's turn in place for a bit, turning in place, and now let's go to holonomic mode. And careful here because it's easy to crash the robot. So moving forward, and a little bit crabby style motion. Okay, moving like a little crab. Look at the wheels in Arvis, how they spin. Really cool. I really like holonomic motion. It's very convenient. Parallel parking, all these kind of things can happen. Okay, so there you go. We have a robust ROS2 control compliant plugin, production ready, that does all the inverse kinematic computation for us. So let's see a little bit about further enhancements, right, for production robots. So steering optimization, so minimize wheel rotation, enable smoother turns. We could also add rate limiting to prevent jerky motion, so limit the difference between the commands. We could do speed normalization to keep the wheel speed limits within the physical limits, reduce oscillations with filtering. We could add fault handling, PID feedback, diagnostics. All of these things could be added to the C++ code. We didn't because it's out of the scope of this lesson, but to make it even more robust and production ready, we could add these things to the C++ controller that we just implemented. So there it is. We have a very robust production ready ROS2 control plugin that you can use with your robot. So in the next lessons, we are going to move everything to Isaac Sim. We've been working with Gazebo this time, and now it's time to connect everything with Isaac Sim. So see you there.